Hello, Chris Gottwald here. Today we're going to be deconstructing the historiographic paradoxes and, oh, wait, wrong topic. We're going to be talking about candidate set designs, tailoring DOE constraints to the problem. So industrial experimentation for product and process improvement has a long history with many threads that I admit I only know a tiny sliver of. The idea of using observation for product and process innovation is as old as humanity itself. It received renewed focus during the Renaissance and Scientific Revolution. During the subsequent Industrial Revolution, science and industry began to operate more and more in lockstep. In the early 20th century, Edison's lab was an industrial innovation on a factory scale, but it was done, to my knowledge, outside of modern experimental traditions. Not long after R.A. Fisher introduced concepts like blocking and randomization, his associate and then son-in-law, George Box, developed what is now probably the dominant paradigm in design of experiments, with the most popular book being Statistics for Experimenters by Box, Hunter, and Hunter. The methods described in Box, Hunter, and Hunter are what I call the taxonomical approach to design. So suppose you have a product or process you want to improve. You think through the things you can change, the knobs you can turn, like temperature, pressure, time, ingredients you can use, or processing methods that you can use. These things become your factors. Then you think about whether they're continuous or nominal, and if they're nominal, how many levels they take, or the range you're willing to vary them if a factor is continuous. Then you figure out the name of the design that most easily matches up to the problem and resources that fits your budget. That design will have a name like a Box-Benken design, a fractional factorial, or a central composite designs, or possibly something like a Taguchi array. There will be restrictions on the numbers of runs, the numbers of levels of categorical factors, and so on. So there will be some shoehorning the problem at hand into the design that you can find. For example, factors in the BHH approach, Box, Hunter, and Hunter approach, often need to be whittled down to 2 or 3 unique values or levels. Despite its limitations, the taxonomical approach has been fantastically successful. Over time, of course, some people have asked if we could still do better. And by better, we mean to ask ourselves, how do we design our study to obtain the highest quality information pertinent to the goals of the improvement project? This line of questioning led ultimately to optimal design. Optimal design as an academic research area was started in parallel with the Box School in the 50s and 60s, but for various reasons remained out of the mainstream of industrial experimentations until the custom designer and JMP. The philosophy of the custom designer is that you describe the problem to the software. It then returns you the best design for your budgeted number of runs. You start out by declaring your responses along with their goals, like minimize, maximize, or match target, and then you describe the kinds of factors you have, continuous, categorical, mixture, etc. Categorical factors can have any number of levels. You give it a model that you want to fit to the resulting data. The model assumes a least squares analysis and consists of main effects, interactions, and polynomial terms. The custom designer makes some default assumptions about the nature of your goal, such as whether you're interested in screening or prediction, which is reflected in the optimality criterion that is used. The defaults can be overridden with a red triangle menu option if you're wanting to do something different from what the software intends. The workflow in most applications is to set up the model, then you choose your budget, click Make Design. Once that happens, JMP uses a mixed continuous and categorical optimization algorithm solving for the number of factors times the number of rows terms. Then you get your design data table with everything you need except the response data. This is a great workflow as the factors are able to be varied independent from one another. But what if you can't? What if there are constraints? What if the value of some factors determine the possible ranges of other factors? Well, then you can define some factor constraints or use a disallowed combinations filter. Unfortunately, while these are powerful tools for constraining experimental regions, it can still be very difficult to characterize constraints using these. Brad Jones' DOE team, Ryan Lekovitz, Joseph Morgan, and Caleb King, have added an extraordinarily useful new feature that makes handling constraints vastly easier in JMP 16. These are called candidate or covariate runs. What you can do is, off on your own, create a table of all possible combinations of factor settings that you want the custom designer to consider. Then load them up here And those will be the only combinations of factor settings that the designer will look at. The original table, which I call a candidate table, is like a menu of factor settings for the custom designer. This gives JMP users an incredible level of control over their designs. What I'm going to do today is go over several examples to show how you can use this to make the custom designer fulfill its potential as a tool that tailors the design to the problem at hand. Before I do that, I'm going to get off topic for a moment and point out that in the JMP Pro version of the custom designer, there's now a capability that allows you to declare limits of detection at design time. If you enter non-missing values for the limits here, the custom designer will add a column property that informs the generalized regression platform of the detection limits, and it will then automatically get the analysis correct. This leads to dramatically higher power to detect effects and much lower bias in predictions. But that's a topic for another talk. Here are a bunch of applications that I can think of for the candidate set designer. The simplest is when ranges of a continuous factor depend on the level of one or more categorical factors. Another example is when we can't control the range of factors completely independently, but the constraints are hard to write down. There are two methods we can use for this. One is using historical process data as a candidate set, and then the other one is what I call filtered designs, where you create a giant initial data set using random numbers or a space-filling design, and then use row selections and scatter plots to pick off the points that don't satisfy the constraints. There's also the ability to really highly customize mixture problems, especially situations where you've got multi-layer mixturing. This isn't something that I'm going to be able to talk about today, but in the future, this is something that you should be looking to be able to do with this candidate set designer. You can also do nonlinear constraints with the filtering method the same way as you can do other kinds of constraints. It's very simple, and I'll have a quick example at the very end illustrating this. So let's consider our first example. So suppose you want to match a target response in an investigation of two factors. One is an equipment supplier, of which there are two levels, and the other one is the temperature of the device. The two different suppliers have different ranges of operating temperatures. Supplier A's is more narrow of the two, going from 150 to 170 degrees Celsius, but is controllable to a finer level of resolution of about 5 degrees. Supplier B has a wider operating range going from 140 to 180 degrees Celsius, but is only controllable to 10 degrees Celsius. Suppose we want to do a 12-run design to find the optimal combination of these two factors. We enumerate all possible combinations of the two factors in 10 runs in a table here, just creating this manually ourselves. So here's the 5 possible values of machine type A's temperature settings. And then down here are the 5 possible values of type B's temperature settings. We want the best design in 12 runs, which exceeds the number of rows in the candidate table. This isn't a problem in theory, but I recommend creating a copy of the candidate set just in case, so that the number of runs that your candidate table has exceeds the number that you're looking for in the design. Then we go to the custom designer, push select covariate factors button, select the columns that we want loaded as candidate design factors. Now the candidate design is loaded and shown. Let's add the interaction effect, as well as the quadratic effect of temperature. Now we're at the final step before creating the design. I want to explain the two options you see in the design generation outline node. The first one, which will force in all the rows that are selected in the original table or in the listing of the candidates in the custom designer. So if you have checkpoints that are unlikely to be favored by the optimality criterion and want to force them into the design, you can use this option. It's a little like taking the same rows and creating an augmented design based on just them, except that you are controlling the possible combinations of the factors in the additional rows. The second option, which I'm checking here on purpose, allows the candidate rows to be chosen more than once. This will give you optimally chosen replications and is probably a good idea if you're about to run a physical experiment. If, on the other hand, you are using an optimal subset of rows to try to fancy new machine learning algorithm like SVEM, a topic of one of my other talks at the March Discovery Conference, you would not want to check this option if that was the case. Basically, if you don't have all of your response values already, I would check this box, and if you already have the response values, then don't. We set the sample size to 12 and click Make Design. The candidate design in all its glory will appear, just like any other design made by the custom designer. As we see in the middle jump window, jump also selects the rows in the original table chosen by the candidate design algorithm. Note that 10, not 12 rows were selected. On the right, we see the new design table. The rightmost column in the table indicates the row of origin for that run. Notice that original rows 11 and 15 were chosen twice and are replicates. Here is a histogram view of the design. You can see that the different values of temperature were chosen by the candidate set algorithm for different machine types. Overall, this design is nicely balanced, but we don't have 3 levels of temperature in machine type A. Fortunately, we can select the rows we want forced into the design to ensure that we have 3 levels of temperature for both machine types. Just select the row you want forced into the design in the covariate table, check Include All Selected Covariate Rows into the Design option, and then if you go through all of that, you will see that now both levels of machine have at least 3 levels of temperature in the design. So the first design we created is on the left, and the new design forcing there to be 3 levels of machine type A temperature settings is over here to the right. My second example is based on a real data set from a metallurgical manufacturing process. The company wants to control the amount of shrinkage during the sintering step. They have a lot of historical data and have applied machine learning models to predict shrinkage, and so have some idea what the key factors are. However, to actually optimize the process, you should really do a designed experiment. As Laura Castro Shiloh once told me, causality is a property not of the data, but of the data generating mechanism. And as George Box says on the inside cover of Statistics for Experimenters, to find out what happens when you change something, it is necessary to change it. Now, although we can't use the historical data to prove causality, there is essential information about what combinations of factors are possible that we can use in the design. We first have to separate the columns in the table that represent controllable factors from the ones that are more passive sensor measurements or derived quantities that cannot be controlled directly. A glance at the scatter plot of the potential continuous factors indicates that there are implicit constraints that could be difficult to characterize as linear constraints or disallowed combinations. However, these represent a sample of the possible combinations that can be used by the candidate designer quite easily. To do this, we bring up the custom designer, set up the response, elect to load up some covariate factors, select the columns that we can control as DOE factors, and click OK. Now we've got them loaded. Let's set up a quadratic response surface model as our base model. Then select all of the model terms except the intercept. Then do a Control plus right click and convert all those terms into if possible effects. This, in combination with the response surface model chosen, means that we will be creating a Bayesian I-optimal candidate set design. Check the box that allows for optimally chosen replicates and choose a sample size. It then creates the design for us. If we look at the distribution of the factors, we see that it has tried hard to pursue greater balance. On the left, we have a scatterplot matrix of the continuous factors from the original data, and on the right is the 100-row design. We can see that in the sintering temperature, we have some potential outliers at 1220. One would want to make sure that those are real values. In general, you're going to need to make sure that the input candidate set is clear of outliers and of missing values before using it as a candidate set design. In my talk with Ron Kennett in the March 2021 Discovery Conference, I briefly demo how you can use the outlier and missing value screening platforms to remove the outliers and replace the missing values so that you could use them at a subsequent stage like this. Now suppose we have a problem similar to the first example where there are two machine types, but now we have temperature and pressure as factors, and we know that temperature and pressure cannot vary independently, and that the nature of that dependence changes between machine types. We can create an initial space-filling design and use the data filter to remove the infeasible combinations of factor settings separately for each machine type. Then we can use the candidate set designer to find the most efficient design for this situation. So now I've been through this. So now I've created my space filling design. It's got 1,000 runs, and I can bring up the global data filter on it and use it to shave off different combinations of temperature and pressure so that we can have separate constraints by machine type. So I use the lasso tool to cut off a corner in machine B, and I go back and I cut off another corner in machine B. So machine B is the machine that has kind of a wider operating region in temperature and pressure. Then we switch over to machine A, and we're just going to go use the lasso tool to shave off the points that are outside its operating region, and we see that its operating region is a lot narrower than machine A's. And here's our combined design. From there, we can load that back up into the custom designer, put an RSM model there, then set our number of runs to 32, allowing covariate rows to be repeated. And it'll crank through. Once it's done that, it selects all of the points that were chosen by the candidate set designer. And here we can see the points that were chosen. They've been highlighted, and the original set of candidate points that were not selected are gray. We can bring up the new design in the and just fit y by x, and we can see a scatter plot where we see that the machine A design points are in red. They're in the interior of the space, and then the type B runs are in blue. It had the wider operating region, and that's how we see these points out here further out for it. So we have quickly achieved a design with linear constraints that change with a categorical factor without going the annoying process of deriving the linear combination coefficients. We've simply used basic JMP 101 visualization and filtering tools. This idea generalizes to other nonlinear constraints and other complex situations fairly easily. So now we're going to use filtering and multivariate to set up a very unique new type of design that I assure you have never seen before. Let's go into the lasso tool. We're going to cut out a very unusual constraint. And we're going to invert selection. We're going to delete those rows. Then we can speed this up a little bit. We can go through and do the same thing for other combinations of x1 and the other variables. carving out a very unusual shaped candidate set. We can load this up into the custom designer, same thing as before, bring our columns in as covariates, set up a design with all high order interactions made if possible with 100 runs. And now we see our design for this very unusual constrained region that is optimal given these constraints. So I'll leave you with this image. I'm very excited to hear what you were able to do with the new candidate set designer. Hats off to the DOE team for adding this surprisingly useful and flexible new feature. Thank you.